Okay, so, like when we're trying to track how a ball moves through the air in physics, it's not exactly a straight line, right?
Right.
But calculus, it actually has this cool trick for understanding those kind of curvy paths.
Mm.
It's called implicit differentiation.
Yeah, and the really neat thing about this technique is that it helps us study these relationships that aren't like laid out in a super clear way. Like imagine you're trying to find the slope of a tangent line to a curve, but the equation for the curve is being a little, well, a little sneaky.
Sneaky. How so? Break it down for me.
So many curves, they just don't want to follow that nice FX rule.
Right.
They like to keep X and y'all mixed up together,
Hmm.
which makes it tough to just isolate Y and use our
Okay.
usual differentiation tool.
Okay, yeah, I see the problem now.
Yeah.
So how do we actually get that tangent line slope when the equation is being so difficult?
Let's look at an example to make it a bit more concrete. So say we have this curve, and it's defined by the equation y6x star of e equals 3. Now, if we want the slope of the tangent line at, let's say, the point -3 on this curve, our usual methods kind of fall apart because we've got her tangled up with x.
Right, because we can't just rearrange it to get that nice y equals form. So is that where implicit differentiation comes in?
Exactly. It's like the I guess you could say the detective of calculus. It helps us figure out these hidden relationships.
Yeah.
So instead of trying to rip you away from X, we just accept that they're kind of meant to be together
Okay.
and we differentiate implicitly.
Okay, I like it. I'm intrigued, but I'm also a little intimidated. So walk me through it a little bit.
Okay. Imagine that Y is like a celebrity who just refuses to be photographed directly.
Okay, I like that.
We just have to observe them, through how they interact with X.
Uh-huh.
So we basically treat Y as if it is a function of X, even if we don't have a nice little formula for it.
So we're acknowledging that there's some kind of relationship there, even if y is trying to be all incognito.
Yeah, exactly. Now, the key here is to remember the chain rule.
Oh, yes, of course.
Whenever we differentiate a term with y in it, we multiply by dx. So we're basically saying, like, y has its own little rate of change with respect to x.
Ah, the chain rule. It's like those
Yeah.
Russian nesting dolls. There's always another layer.
Yeah.
So, like, if we differentiate u, we don't just get 3y meta x.
You got it. We get 3y minutes to dx. We got to say, hey, y is involved here, and we got to consider how fast it's changing, too.
Right, because that dx, that's actually the slope of the tangent line that we're hunting for.
Exactly. Now, if we apply this to our whole equation that y6xx or x equals 3, what we get is 3y6 12x equals 3. We've got our dx.
And so now we just isolate it, solve for it, and bam, we've got our slope. Right.
Not bam just yet, but we're close. That equation actually gives us like a general expression for the slope, but it works at any point on our curve.
Okay, so how do we go from that general expression to the specific slope at the point we care about, -2, 3?
And this is where things get really cool. Remember how we were thinking about y as a function of x?
Yeah.
Well, now we can actually use the specific x and y values from our point and plug them in.
Okay, so let me try this out. If we plug in x equals 2 and y equals 3 into our differentiated equation, we end up with 27, 3x, plus 24 equals 0.
Perfect. And if you solve for dx, you'll see that the slope of our tangent line at the point -2, 3 is actually -89.
Okay.
Now, you might be thinking, why go through all this trouble if we could have just, maybe solved for y in the original equation?
Yeah, it does seem like extra work if we could just rearrange things.
But here's the beauty of it. This method lets us find those slopes even when solving for y is a nightmare or, straight up impossible. It opens up a whole new world of curves that we can analyze.
Okay, yeah, I'm starting to see how powerful this is. We've only looked at one point on our curve so far. What happens when we want to understand how this curve behaves at multiple points? That's when things get really wild, right?
You're exactly right. It does get pretty interesting. Let's say we want to see where our curve intersects with the vertical line x obliques 1.
Okay, so we're basically fixing x and seeing what Yoi does at that spot. It's kind of like we're taking like a vertical slice right through our curve.
Yeah, exactly. We're focusing our analysis on a specific cross-section of the curve.
So how do we actually find those points where they intersect?
We're going to go back to our original equation for the curve, remember? It's y6x dot equals 3, and we're literally going to plug in x equals 3.
Okay, let me think. That would give us y6 equals 3, and then simplifying that a bit, we get y9 equals 3. Oh, okay, so now we have ourselves a cubic equation.
And just like that, we've turned our intersection problem into solving for y in a cubic equation.
And then after a little bit of factoring, or maybe, asking our calculator for a little help, we find that there are actually three solutions for y. 1, 1 plus 2, and 1A2.
Which means our curve is actually crossing that line, x equals 1, at 3 different points. Each of those y values, when we pair them up with x equals 1, they give us coordinates for an intersection point.
Well, wait. 3 intersection points. So, like, we could draw 3 different tangent lines right there.
Exactly. And each of those tangent lines is going to have its own slope that'll tell us something about what the curve's doing at that exact intersection.
Okay, this is pretty cool. So if we find that the slope is positive at one of the intersections, that means our curve is increasing as it passes through that point.
You got it. Positive slope, it's like it's going uphill, right?
Right.
And then a negative slope, obviously, that would mean it's decreasing, heading downhill at that intersection.
Which reminds me of when we used the first derivative test in regular calculus.
Yeah.
To find those peaks and valleys, those local maxima and minima.
Exactly. You're making great connections. It's like, just like the first derivative can tell us if a function is going up or down, the slopes of these tangent lines are giving us localized details about our curve's behavior.
This is so cool. We've gone from one little tangent line to a whole bunch of them, all showing us different sides of how this curve behaves. But before we get too caught up in tangents, is there anything else we can do with this implicit differentiation stuff to learn even more about this curve?
Oh, there's always more we can explore. Remember that second derivative in calculus? Well, we can use that here too to dig a bit deeper into the curve's curvature.
Wait, you mean we're going to differentiate the equation that we already differentiated? What does that tell us?
It tells us all about the rate of change of the slope, which can reveal whether our curve is concave up like the inside of a bowl or concave down like the top of a roller coaster hill at a specific point.
So it's like the first derivative, that's like checking the speedometer of the curve. Is it going up or down? And the second derivative, that's like checking the accelerator, figuring out if that rate of change is changing.
Love the analogies. Like, we're not just watching the curve's path anymore. We're actually understanding the forces that are making it move the way it does. And we can even find those second derivatives at those intersection points, too, to get super detailed insights.
This is incredible. We've basically cracked the code to understanding complex curves.
And the really exciting thing is that this is only scratching the surface. Implicit differentiation, it can be used for way more than what we've talked about. We see it pop up in physics, engineering, economics, you name it.
Okay, now I'm super curious. Can you give me an example? How does this actually play out in the real world?
Well, imagine you're designing a roller coaster.
Okay, there we go. My favorite real-world example.
So that roller coaster track, it's got to follow a very specific curve, right? And you know those curves aren't always going to be nice and neat, like y equals f of x.
Yeah, because we've got loops and corkscrews, those suddy drops. Those are some pretty intense curves.
Exactly. And those engineers, they need to understand every single twist and turn to make sure that coaster is exciting, but also safe, right? That's where implicit differentiation comes in handy.
So they're using it to figure out the actual forces that are like acting on the coaster at any given point.
That's it. They can find the slope of the tangent at any point, which tells them the direction. And then they can even use the second derivative to learn about the curvature.
Oh, wow. Okay, so it's like implicit differentiation is literally keeping roller coasters on the tracks. I knew this stuff was powerful, but that's pretty amazing.
And it goes way beyond roller coasters too, you know? Anytime you've got a system where the variables are connected in some kind of complicated way, you can use implicit differentiation. Could be anything like how a comet moves through space, how fluids flow, even like the stock market.
This deep dive has been quite the adventure. We started with the slope of a tangent line, and now we're talking about all these really complex real-world applications. I definitely feel like I've learned a lot about calculus today.
I hope you've also gained a new appreciation for how elegantly implicit differentiation helps us understand these hidden relationships. It's like sometimes the coolest discoveries happen when we really lean into the complexity instead of being afraid of it.
That's such a good point. So if you could leave our listeners with one thing to think about after today's deep dive, what would it be?
I'd challenge them to just, try to notice these kind of implicit relationships in their everyday lives. It doesn't have to be as complicated as a roller coaster. Like, think about the shape of, a flower petal or the curve of a bridge, even how shadows change as the sun moves. These things, they all involve these implicit relationships that we've been talking about. It reminds us that calculus isn't just something you learn in a classroom. It's all around us.
That's a really cool thought. It's like we've unlocked this whole hidden language for understanding the universe. Well, thank you so much for guiding us through this incredible deep dive. It's been a pleasure.
The pleasure was all mine. Just remember, the learning never really stops, and there's always something new to discover, something to ask about, and something to understand better.
And who knows what other amazing math concepts are out there waiting for us to explore. Thanks for joining us on the deep dive. Until next time, keep those brains working and that curiosity alive.